Hello, my name is Javia Muskan. I'm going to give a seminar on a low-code federated learning. Coming to the learning about what is federated learning. Federated learning is a distributed learning paradigm where multiple clients train their machine learning models with the coordination of a centralized server. It is a collaborative machine learning without the centralized training data. It is a new distributed training technique that provides in-situ training on decentralized edges. And AI requires a tremendous resources and efforts regardless of levels of expertise. And federated learning has empowered a wide range of application with privacy preserving mechanism, including healthcare application, consumer products, recommendation system, and video surveillance. And federated learning has uh, experienced researchers. Beginners who are interested in federated learning face high barriers to entry due to the complex setup and non-trivial concepts. Researchers with a lesser practical experience in the federated learning would need 2 to 3 weeks to build a vanilla federated learning application from scratch and understand the other complex features of it. Experienced researchers face challenges building prototypes and deploying federated learning applications because they may not be familiar with the software engineering and infrastructure. So FedAverage is one of the standard federated learning algorithm. It is a default algorithm and it is easy to implement, and it completes the training with the 3 steps. And here is the equation for the Fed average. F of W is equals to summation of K is equals to 1 to K, F of K of W. And federated learning platforms. These are the federated learning platforms. Institutions and companies have developed various experimentation-oriented federated learning platforms and frameworks. The one is LEAF, another is TFF, and another is FATE. LEAF is an experimentation-oriented algorithm, provides sample implementation and simulates statistical heterogeneity with federated databases, but they lack deployability. And coming to the TFF, it is a deployable research-oriented platform, but it doesn't optimize distributed training. FATE is an industrial level framework, supports deployability, and is not user-friendly due to high barriers of entry caused by heavy system design. So federated learning life cycle. Coming to the federated learning life cycle, there are basically 2 phases in federated learning life cycle. So one is an experimental phase and one is a production phase. Coming to the experimental phase, these are the following steps in the phase: identification of the problem, set up the simulation environments, adapt the existing algorithms and develop new algorithms, and conduct experiments with different combination and hyperparameters and analyzing the results. Production phase, after deployment, the algorithms are evaluated under the real world scenarios in this phase. The key step to transmit from experimental phase to the production phase is the deployment. Following is the steps in this phase: collecting and transforming the data in clients, adapt the data sets to federated learning system, train and evaluate the algorithm developed in the experiment phase, analyzing the results and publishing the model for survey. Coming to the low code federated, the main one of we have now till now we have learned about the federated learning, and now is the EasyFL, that is the low code federated learning. And the main objective of this is to train the AI model without anyone seeing or touching the data, offering a way to unlock information to feed new application, and train a machine learning algorithm for instant deep learning networks on a multiple local data sets contained in a local nodes without explicitly exchanging the data samples. And this is the proposed system, that is a low-code federated learning, that is EasyFL, to enable the users of various expertise to experiment and prototype federated learning application with little coding. And this EasyFL empowers them with the out-of-the-box functionalities to accelerate experimentation and deployment. EasyFL not only requires just only 3 lines of code to build a vanilla FL, but also incurs the low training overhead. And EasyFL, learning more about the EasyFL, that is a low-code federated learning. This enables the users of various expertise to experiment and prototype federated learning applications. Beginners can start only with 3 lines of code without any knowledge of federated learning. For researchers who are addressing the advanced and the open problems in federated learning, this provides them with sufficient flexibility to develop new algorithms with minimal coding by reusing the majority of federated learning architecture, empowers experienced researcher researchers to easily prototype and seamlessly deploy federated learning applications without further engineering. This particular goal is achieved ensuring the greater flexibility and extensibility for customization by unifying simple API design, modular design, and granular training flow abstraction. This is a low training overhead compared to other popular federated learning libraries, accelerates distributed training by 1.5x under the limited hardware resources, and it is user friendly and support efficient experimentation. EasyFL architecture basically has two parts: interface layer and the modularized system layer. Interface layer, this provides APIs, simple APIs for the high-level applications, key design that enables low-code capability. It contains APIs that are designed to encapsulate complex implementation from the users. The APIs here decouple application-specific model, datasets, and algorithms such that EasyFL is generic to support a wide range of applications. Coming to the system layer, it has complex implementation to accelerate training and shorten deployment time with the out-of-the-box functionalities, and supports and manage the federated learning life cycles. And it has 8 modules to support the federated learning training pipeline and life cycle. That is simulation manager, data manager, model manager, server and client, distribution manager, tracking manager, deployment manager, and lastly training backend. And the APIs that the EasyFL used are categorized into 3 categories: initialization, registration, and execution. And EasyFL algorithm, there are many EasyFL algorithms, but coming to this algorithm, EasyFL accelerated distributed training under heterogeneous simulation and resource constraints in the distribution manager. EasyFL enables the distributed training optimization with only one line change in configuration. It allows the training with the number of selected clients larger than available hardware resources by allocating multiple clients into one hardware to conduct training. The allocation is not trivial because the training of the clients could vary dramatically under the system heterogeneity or unbalanced data. So the EasyFL basically uses the greedy allocation. Basically, okay, the problem statement here is assuming the training times of all the client times. Clients are known and describe the problem as the following. That is, given the input is number of GPUs M, a set of training of N clients where N is greater than or equal to M. And greedy allocation with adaptive profiling is one of the algorithms that EasyFL uses. And the problem is a variant of multiprocessor scheduling problem, which is a NP hard optimization problem. We adopt to the greedy allocation, that is longest processing time algorithm to solve the problems, sort the clients in descending order by training time, and allocate the slowest client to the GPU with the shortest total time. However, the training time for each client is unknown at the beginning of the training. So use an adaptive strategy to update the training times of clients instead of profiling at the clients at the start of the training, because profiling would consume intolerable time with total clients are large. We summarize the algorithm of greedy allocation and adaptive profiling, which is termed as greedy allocation with adaptive profiling. Greedy EDA updates the training time of the selected clients and marks them as profiled after they complete each round of training. It then updates the training time of the non-profiled clients with the moving average of selected clients training time and the preset default uh, training time T. The hyperparameter default client training time is to support the efficient training during profiling by mitigating extreme long or the short training time of clients. Users can either set the default client's training time by the estimated average training time if they are familiar with the task, or set the updated momentum M is equals to 1 to disable if they are uncertain about the time. The latter may occasionally lead to the extreme case in only one round of the randomness of client selection, but it does not have much impact when the majority of clients are profiled after several training methods. So coming to the results of this. Okay. This slide shows the results. Like first this thing shows the training time comparison of standalone and distributed training using 3 data sets, that is Feminist, Shakespeare, and Cipher 10. And the greedy allocation with adaptive profiling effectively rates training on all the data sets. And it is run on we run the experiments with 20 selected clients per round and the simulated heterogeneous scenarios. And this is the data sets and model provided by EasyFL to simulate statistical heterogeneity. Like this is the data sets and number of samples, number of lines, and the models that are used to train it. Thank you.